Speaker is Siddhartha Mukherjee, who is a postdoc at ICTS, and he will talk about Lagrangian anomalies abound in aqueous conditions. You are ready?
Yeah. Can I start? All right. Thanks for the introduction. So I want to tell you about some work we've been doing in active turbulence, in particular about some Lagrangian anomalies which we found lurking in these systems. So let me just try. Yeah. Yeah, thank you. So what is the system? Basically, when you have a dense suspension of certain bacteria, it can give rise to collective states of motion, which are very complex in space and time. And they sort of resemble what we know from inertial turbulence. And what's also interesting is that if you coarse grain the system, you can also describe it with a sort of a generalized hydrodynamics equation. This is basically similar to your Navier-Stokes equation, but there are some additional terms, there are some changes. And this was proposed in this work who looked at experimental bacterial systems, and they wanted to suggest a model which very closely mimics both qualitatively and quantitatively what you see over there. So essentially what you have is a generalized advective nonlinearity. So it appears with the lambda coefficient here. You have a higher order Laplacian term. So you have two terms which give pattern formation in Fourier space. And you have an equivalent terms also called the Toner 2 drive, which adds, you can basically add friction to the system, you can inject energy. And the last term here, beta, will always sort of stabilize the system. So for the purpose of our talk, the main parameter will be alpha. So I'm just going to maybe focus on that. And add to this Lagrangian tracers, which you see here, which basically just follow a very simple equation for, let's maybe move this here. So your tracers just follow a very simple equation. They follow the flow field. And if you solve this, you get tracer trajectories, which can look like this. You have convoluted motion and your tracer evolves. And if you calculate the mean square displacement, which is just the average displacement of the tracer from its initial location, and you ensemble average that, you get a very classic ballistic to diffusive transition. So things start scaling proportionally to T over time, which is your diffusion. Now, this is okay, but what was found is that experimentally, more interesting things can happen because nature is more rich in phenomena. And what they found was that as the same bacterial system under maybe some other conditions, it can perform Levy-Walks, and which gives rise to anomalous diffusion. So what are Levy-Walks? They are similar tracer movements, but now there's a combination of persistent motion with convoluted motion. The convoluted motion gives you diffusion, persistence can be ballistic, so you get a diffusion coefficient which is between 1 and 2. That's anomalous diffusion. And it has been proposed that this sort of movement might be more useful for efficient foraging and evasion of hostile environments. So it's certainly, it's not the coefficient, sorry, it's, I mean the coefficient, the exponent, sorry, not the coefficient. And what we wondered was why has this not been seen in simulations of active turbulence? And secondly, other Lagrangian anomalies, because clearly if this is happening, this will also influence all sorts of other Lagrangian things we want to study. So we play this game of basically simulating the system using this equation, and we only focus on alpha. We want to increase the activity and see what happens. So I want to start off by showing you what happens to a bunch of tracers, which will evolve in two flows. One of them is mildly active turbulence, one is highly active turbulence. And this you can think of as a drop of ink in the middle of the domain, which is being moved around by the underlying flow. And you'll see very quickly, very beautifully, the tracers are able to pick out the vertical patterns and they sort of diffuse out. That's what's, so the colors are just to represent mixing. So I start the tracers as yellow and blue, and in the end, if you see where blue ends up and where yellow ends up, that gives you an idea of how mixing is happening in the system. So it's just for visualization. On the right-hand side, you see something very different. I mean, the motion is markedly different from on the left. You have these persistent material lines that just propel further, and then they suddenly twist and move around. So clearly something very different is happening. Just by increasing the level of activity, the motion of the tracers has changed significantly. So the question is, what does this do, of course, to the statistics? So let's look at the mean, yeah. Yeah, because alpha appears with a minus sign on the right-hand side. The negative value of alpha is more injection of energy. Yeah. So here you see mean square displacements for different values of alpha. So positive alpha is friction, negative alpha is active injection. And this arrow shows you the direction of increasing injection of energy. And you see that for friction and for mild levels of activity, you have your classic ballistic to diffusive transition, so T square to T. But at very high levels of activity, you get a very robust regime of anomalous diffusion almost over 2 decades in time. So clearly there is super diffusion in the system. The question is, what is causing it? Is this happening through some Levy walks? For that, we need to look at statistics of individual trajectories. So you need to segment your trajectory into what are known as walking segments. It's fairly simple to do that. You just mark turns. So as soon as your particle makes a sharp turn, you mark that as a point, and then you calculate the time between successive turns, and you can measure the distance. And you want to look at the distribution of these, what is known as the waiting time. So that's the time between 2 turns. And if you plot that out, you also see a power law distribution of these. And that has an exponent here, which is close to -8/3. Now, why that is important is because from Levy walk theory, we know that the exponent for the mean square displacement is closely related to the exponent of waiting times. And they together add up to a theoretical constraint, which is within numerical error. It's satisfied in our system. So we can say that this is happening while Levy walks. So that's the first Lagrangian anomaly. What else is happening? Basically, we have this whole bunch of tracers in this flow. There are many, many tracers. And we also want to visualize. I mean, we want to see what does persistent motion look like? What does diffusive motion look like? So what we can do is, for each tracer, we define a certain distance of travel. And we see how long the tracer takes to reach there. And then we sort the tracers based upon how long it took them. And we can pick the top 1% and the bottom 1%, so the fastest and the slowest. So I just want to show you what that looks like to start with. We've artificially brought all the tracers to a common center just for visualization. So now they reach out to this big circle around them. And the colors here just represent the angle at which they are going to hit the target. So something very interesting emerges here. You see that the persistent tracers, they also bundle together. So it seems like there are certain regions in the flow that if you start over there, you're going to move together. So you see bundling in this direction, there is some bundling over there, and the distribution is highly anisotropic. So these are the most persistent tracers. Whereas the diffusive ones, you see it still goes on, it takes them forever to reach the circle. So the ensemble has the behavior of both persistent and diffusive trajectories. And in fact, each trajectory will have a part which is persistent and which is diffusive. It's not like you'll have unique trajectories like that. And we want to quantify this a bit further, which is closely related to the first passage problem or survival probabilities. So you take circles of increasing radii like this, and you just measure the time it takes for a tracer to hit a small circle, then a big one and a bigger one. And you see the distribution of these times. So if you look at typically a diffusive suspension, which is at mild levels of activity, so the inset shows you all the distribution times. So for bigger circle, of course, the distribution widens. But if you normalize it by r square, which is the radius of the circle, all of these curves collapse. That's because the suspension is diffusive. We know that distance goes with the square root of time. So r square will collapse all of these. But what happens to this in a super diffusive suspension? So in the case of anomalous diffusion, you get 2 regimes. For small to intermediate values of r, you get an anomalous collapse, which goes with r3/2, which is again consistent with the mean square displacement scaling. And once r becomes large enough, again diffusion takes over, and everything again starts scaling with r square. And so this is the second Lagrangian anomaly, and we found a third, which is in pair dispersion, and also in chaotic measures like Lyapunov exponents and so on. So I want to talk about one last thing in this talk, which is a very interesting question, in that can we trace these Lagrangian anomalies to anything in the Eulerian fields? Because you have a flow which is also changing, and you have a bunch of tracers. So can we find certain features? Are they causing this in some way? So let's just look at the fields for once. You already saw the one on the left, that's mildly active turbulence. On the right, you have this highly active turbulence case. And there are clear differences. One of the things is there's a larger scale circulation going on. Smaller vortices move faster. But if you look closely, you also see these sort of banded streak-like patterns, which don't have an analog in mildly active turbulence. And actually, they also don't have any analog in inertial turbulence. They are sort of a feature of maybe this system. So now here's an observation. You increase activity and 2 things happen, at least 2 things. you get anomalies in Lagrangian measurements, and you get these strange features in the Eulerian fields. So the natural question is, are these two related? So you can try to take a hint at that by here. I just zoom into a small portion just to show you these streaks, and also here just the spots of vortices. And you just plot the streamlines of velocity. So this is a frozen field, right? I mean, this does not give you the full picture because the system is very dynamic. This field changes very quickly. But even on a frozen field, your streamlines are very coherent here. You get this persistent motion. So clearly, if a tracer starts here, it's going to move persistently. Whereas if you're here, then your vortices are just turning you around all the time, and you get diffusion. So it gives us a hint that they might be related. So can we quantify this further? For that, we need, of course, a criterion to define these streaks. And you can come up with your criterion. We came up with something which is quite ad hoc. But the point is, with some accuracy, it helps us isolate these patterns. And now you have something interesting because you have a pointwise measure which tells you whether you're in a streak region or whether you're outside of it. So I can take my trajectories, and over time, I can segment it into red and blue, red being outside the streaks, blue being inside the streaks. And once I have that, I can define a residence time in streak regions. I can define a displacement within streak regions and outside of it. And that's exactly what we look at. So you have a joint distribution there of a normalized displacement when the particle is within streak regions, and the x-axis is the residence time, and outside of streak regions. And what you see is that, well, you spend less time in the streaks. That's because these are very sparse. They die off as well. But what you notice that this slope is much steeper. So when you're in the streak regions, you're more likely to travel farther. And this really helps us sort of quantify to some extent that the streaks do aid in persistent motion in our system. So that brings me to the end, basically, and I'd like to summarize by, I mean, there's this nice old adage that if you want to go fast, you go alone. If you want to go far, you go together. It seems that bacteria is aware of this wisdom. So what they do is, I mean, it's the going together which is important, because you have an emergent flow pattern where a lot of small scale motion gets together, and it gives rise to this beneficial, biologically beneficial movement patterns. And we notice these Lagrangian anomalies, and it's closely linked to certain features in the Eulerian fields. What we are doing now is we want to quantify chaos in the system to some extent, also look at fluctuations and intermittency. And of course, we also want to test this in experiments. We want to see how much of this can be found in real bacterial swarms. So we want to do some experiments at NCBS. So Shashi has been extremely kind to welcome us to his lab to try this out. So that's what we're going to do now. And I want to end by acknowledging Rahul Singh, Martin James, and Shumriddhi. We worked together on this. And here are some references for this work. And I've also put my contacts. If you want to discuss this more, I'll be very happy if you write to me. And I'll end there. Thank you for your attention.
Questions?
Interesting. So in one of them, you were showing one of the slides where you were showing two movies. There was one on the left. It was, I think, some two different kind of turbulences. I think the last one.
I see. Yeah.
Active, highly active, and I think mildly active.
Right.
Two cases.
Yes.
Yes. So my curiosity is whether is it possible to identify some length scales of these vortices that
certainly
can actually scale with this activity or whatever.
So one of the things is there, it's fairly easy on the left side, because if you look at the energy spectrum, you typically have a well-defined peak and it's a fairly sharp spectrum. But here it's a little bit more difficult because this is truly a multi-scale spectrum. So you, in fact, get a power law in the energy spectrum as well. So you don't, and that's the interesting thing, because that's like inertial turbulence. You have a range of scales. And we feel that a similar thing is happening here. You also get a range of scales here. So you can define a vortex at several length scales.
One more thing, just to mention about this inertial turbulence. So what separates the inertial turbulence with this activity?
So that's something we want to answer with this. So one of the things is that There are a lot of similarities, a lot of differences. So inertial turbulence does not have these anomalies. If you put tracers in inertial turbulence and you increase the Reynolds number, you do not get super diffusion or something like that. It's the diffusion coefficient which changes, not the exponent. So that's a very major difference.
So these are at low Reynolds number, or
These are all low Reynolds numbers here. Yeah.
thanks.
Yeah.
Yeah. So the super diffusion, does it persist forever, or is there a
No.
length scale? So what is, I missed something. What is the length scale cutoff? It's an intrinsic length scale, right?
What is the length scale for?
What's the length scale beyond which super diffusion crosses over to ordinary? There must be one, right? I mean,
There is certainly. I mean, so for the mean square displacement,
yeah.
if we look at it long enough, so we are almost
I'm just curious, what is that long enough? It's some intrinsic scale, it's not a box size, right?
It's not the box size.
Yeah.
It's much bigger than the box size, but well, it's bigger than the box size, but I don't know where that length is coming from. I mean, it is linked to also, for instance, if you look at the trajectories, then, I mean, this probably does not answer your question, it's an indirect thing, but you have these persistent segments, and where your super diffusion falls off is linked to the extent of the distribution of step sizes.
Yeah, it's the tails of the step size.
Yes.
No, so from your measurements, step size distribution is something whose variance doesn't exist. I mean, over the range you look at, or
so the variance doesn't exist. But if you, I don't know if we do on a much larger domain, maybe then it will cut off, and that would set a length scale. That's possible.
Right.
But up to the domain sizes we looked at, we couldn't get that.
Same question. So I guess this cutoff is probably related to this size of the streaks or whatever, right?
Not necessarily.
Isn't it like they?
Yeah, certainly. I mean, so the question is, if you look at this flow, what is the longest you can go straight?
Yeah.
So it would be related also to how this pattern is changing over time. So that certainly sets a time and a length scale. That's true.
One more question was, so the battery actually itself doesn't follow leading off or anything, right? That has.
Who, sorry?
It's the tracers who.
So but in this case, the tracers and the bacteria are indistinguishable because the bacteria is it is that's right. Yeah.
And one last question is, so how sharp are this so to find the distribution of these times between the tumblings?
Yeah.
So the tumblings are really sharp. Is it like when you
to look for the turns?
Yeah, when it
a little bit. It's not super sharp, but you get some turns that are very clearly sharp. But then you also have some which change slowly. So these distributions should remain constant over a few choices of your cutoff, and that's what we showed that within +10, -10, it more or less gives the same distribution. Yeah.
Other questions? I have one question. So is this super diffusion related to the correlation of the velocity field over space and time? Did you look at the correlation?
Yeah. So we looked at the correlation length. But the thing is that so if you look at the correlation of the velocity, that falls off much faster than the super diffusive length scale. So the velocity remains correlated over a much shorter length scale than you have for.
Is dx dt equal to u?
Yes.
Is this?
Yeah. Because typically when we look for the correlation length, we average over the whole field, right?
Can't I think of this as a motion of a particle in some loop? Can I think of u as a noise, which is a correlated noise? Yes.
I see what you're saying.
Yeah. It has some. So can I model this dynamics of the tracer just by writing down and it's equal to some noise?
Which is correlated in time. Yeah. That's possibly. I think that should be possible. That would need us really to characterize what, Abhishek also asked, is how long does this persist, for instance? What is because that is the correlation length I would want to feed in, because if I just look at the velocity correlation here, that would not work then, because that falls off much faster.
So the velocity, the activity through the velocity equation, doesn't it act as a colored noise and gives you the time scale?
Sorry?
Activity through the velocity equation, doesn't it act as a colored noise and give you the time scale that Anupam is probably trying to?
Activity does set a velocity scale here.
Yeah.
But so there are two things. I mean, you get a velocity scale, which is a pointwise measure, and that is set by the activity. And the other thing is a non-local measure, which is the length of the correlation. And that really comes from the entire dynamics then. So that the activity alone does not set after a while, I think.
Specific to this particular system, there have been examples in 2D Navier-Stokes where you can find an anomalous dispersion with just Ekman friction term, which is your activity parameter here.
Right.
So this paper is from 1993. You might want to take a look at it. They also characterize anomalous dispersion using different kinds of stationary points. Of course, here there are only two,
Okay.
Elliptical and strain-dominated regions. The question I have is, the streaks that you're talking about, can they be characterized as either strain or vertical dominated regions, or are they different?
Yeah, so typically you have an Okubo-wise parameter, which gives you the separation between that. Maybe I can show it quickly. So the streaks actually don't have much of an Okubo-wise, but they do have a bit of vorticity, which is what helped us pick them out, in fact. So if you look at it here, the streaks have certain level of vorticity, so there is at least a lower cutoff for vorticity, but they don't have, I mean, the lambda field, which is omega square minus strain square, that is more or less quiescent, so that sets an upper cutoff. And that's how we managed to define a criteria by saying one will be above. So this is, the streaks don't show up here, so strain is sort of balancing vorticity over there. Yeah. And thanks for pointing out regarding the paper. I'll get it from you. Thanks.
Okay, so let's thank Siddhartha once again.